Hello everyone, welcome. Today we're going to talk about Taylor's remainder theorem, which is also known as Lagrange. And I'm going to try to keep this video as pretty basic as I can. I'm going to do a couple of examples, but the one thing that we just have to really quickly talk about here, because I think that a lot of students get really confused with this error. And I really want to just kind of simplify it, keep it very, very, very basic on what the thing is. So the formula we're going to use for Lagrange is actually written right here, and just to kind of break it down a little bit for you, and I'll give you more examples about this in a minute, but this first part right here I think is the only part that students really struggle with. So with the alternating series test, our error is basically maxed by the next term. So if I was trying to find the error in the fifth partial sum, you would go to the sixth term, and that would be the maximum the error can be. Well, that's exactly what this is right here. So this is going to be the maximum value of our n+1 derivative. All right, and so we'll do a couple of examples and talk about this value, how we can obtain it. The x value that we're going to be using here, that's what we're trying to approximate. The c is going to be the center of your Taylor series, and then the n is going to be our degree that we're trying to find. So if we're looking for a third degree, we're going to do this to the fourth. If we're looking for a fourth degree, we'll do it to the fifth. So I've got a couple of examples that we're going to talk about here, and like I said, I'm going to try to keep this as simple as possible and just kind of go through the problems as we go. All right. So for example number 8 that we're doing right here, and the numbers are weird because this is how I teach it to my students, but in our packet. So it's actually asking us to let f be the function having derivatives of all orders at all real numbers. Really important, it says right here, a third degree polynomial. All right, so a third degree Taylor polynomial for f about x equals -2 is given by our function right here, right, p of n, p of x. And then it says the fourth derivative for the f satisfies the inequality. And it actually gives us this, right? It actually gives us this. Solves the inequality that the fourth derivative will be maxed out at 25. It will be less than or equal to 25 for all values on the interval from -2 to 0. And this is found the Lagrange error bound for this approximation at -1.6. Okay, so the first thing we're going to do is write out the equation for Lagrange, right? So we're going to write out what our equation for this is. And then when we do that, we're going to talk about what we need to do to figure out what we have, right? So this is our equation that we're going to do, and there's really just 3 separate parts for it. And okay, so the first thing that we're going to acknowledge here is that this is our maximum our derivative can be, the maximum value our derivative can be, and it's actually given to us because remember we're looking at a third degree polynomial, right? So this is the third degree polynomial, and so it's already told us that if n is equal to 3, right? So this example, n is equal to 3 because we're looking at a third degree polynomial. Well, it's already told us what our next derivative is. It's already told us that this is going to be the n+1 4. So this is already saying that we're going to be maxed out at 25. So I know that this little piece right here, that's actually going to be equal to 25. That's not always nice that they give this to us, and the next couple examples, they're not going to give it to us, and so I'll show you guys how to find it. But it's really awesome when they actually show us what the number is. Okay, the x value, the x is what we're trying to approximate, right? So again, I'm going to write that out for us. So the x in the equation is what we're trying to approximate. And so in this particular example, we're trying to approximate -1.6. So in this example, our x is going to be -1.6. And then our c here is going to be where we're centering our polynomial. Well, we're looking at the center. So there's a lot of ways they can give us this, but in this case here, they actually give us the actual chain. So c is going to be equal to, now remember that the formula is x minus c, right, when we're looking at the Taylor series. So then our c is actually -2, right? And then the n that we're going to be looking for here, the n in this case is going to be equal to 3. So we actually have everything that we need to actually find this error. So our p of 3 of x is going to be equal to 25 times the absolute value of -1.6 minus a -2, right? And that's all raised to the n plus the 3 plus 1, which is really just 4, right? And that's going to be all over 3 plus 1 factorial. And so that's the general idea of what we have to do for this. So we can simplify this up a little bit more, right? So it's really just going to be 25 over 4 factorial. And then when I look at this right here, it's going to be negative 1.6 plus 2, right? Plus 2. So it's going to basically be 0.4, which is really just 4 over 10 to the 4th power. All right. If this is an FRQ, you leave it exactly like this. There is no reason at all to simplify it. Usually, if it's a calculator question, you just plug this into your calculator, and you're going to get that this is 0.0267. And if you actually use the calculator, you're actually going to get that this is actually 2 over 75. So the error that we're going to get on this particular series for our third degree polynomial is going to be 2 over 75. Okay, so we're going to go ahead and talk about number 9 now. It says a student needs to calculate 1 over the square root of e on a 4-function calculator. He uses a third degree Taylor polynomial. So again, just like the previous example, we know that n is going to be equal to 3. For y equals e to the x, and adds on the Lagrange error. All right. So this question is a two-parter. The first one is we got to find the Lagrange error. We also need to figure out what the actual Taylor series is, like what the value for the Taylor series is going to give us, and then we can add those two things up, and that will give us the results that we're going to need. So let's look at, first of all, the Lagrange error. So just like in the previous example, we're going to write up our equation here for this. So in this case, we're looking at the fact that f of n plus 1 to z, right? And we're going to multiply that times x minus c to the n plus 1. And this is all over n plus 1 factorial. All right? So we already know that n is actually equal to 3. Well, what is our x? What are we actually trying to approximate here? Well, we can rewrite this, right? We can rewrite this because we're asking to find it using the polynomial e to the x. Well, I can rewrite our function as 1 over e to the 1/2. And so I want to make this look like, I want this to look like what we're seeing right here. So we can easily do that by rewriting this as e to the negative 1/2. So that lets us know that x is actually going to be equal to negative 1 over 2, or negative 1/2, right? And so our c value, our center for this, is actually going to be equal to 0, right? So there's no changing in our function for that. So what we need to do here is start plugging stuff in. So now this is the part where we're going to have to find this, right? We need to know what our maximum derivative is going to be when c is equal to 0. So any good calculus student knows that if you take the derivative, right, so our first derivative of e to the x, we get e to the x. If we plug in our c value of 0, we're going to get 1. You guys also know that no matter how many derivatives I do of this, my derivative will always be e to the x, right? So that means that no matter what I do, the highest value, the maximum value this is going to be, is actually equal to 1. So I know that this right here is simply going to be 1. That's not always 1, but in this case it is, right? So we're just going to figure out what's the maximum value it's going to be. And we can also think about it just what's the maximum value for the third degree Taylor polynomial. So then let's go ahead and start finishing up the problem here. So x is going to be equal to negative 1/2. I'm going to subtract c from it, and I'm going to raise this now to the 4th power, right? We'll raise this to the 4th power, and then I'm going to go overhead and do 4 factorial. So really what I have here is negative 1/2 to the 4th degree times 4 factorial, right? And so we're going to use a calculator. We're going to use a calculator to find out that this decimal answer is 0.0026. All right, so this is the error that we were going to get using the third degree polynomial of e to the x. And so the second part to this question is, well, what is the actual value we would get, the approximation we would get for e to the x using the third degree Taylor polynomial. So we all know again that if I'm looking at the series for e to the x, well, that's just going to be equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. All right. Well, I know right now that we're approximating, right, and we automatically know what x is. We know x is negative 1/2, so it's going to be negative 1/2. So we can go ahead and plug in negative 1/2 to our x values. And again, we're going to use a calculator. Use a calculator to find out what this value is right here. And with the calculator, we're going to get the value of this as 0.6042. And so that's the Taylor approximation that we used when x was equal to negative 1/2. So all we have to do now is take the approximation we did from the Taylor series and add the error that we got using Lagrange. And we're going to get the point here, 0.6068, right? So 0.6, and that's written really, really, really small. So let's actually write it up here. So 0.6068. And the interesting thing is, this is what we get as an approximation using our error, using the third degree. And the actual value, if you actually were to plug in 1 over the square root of e in your calculator, is 0.60653. So we were pretty close, not so bad with our answer and approximation, and that's pretty good. So those are two pretty straightforward Lagrange error problems. I'm going to come back and do 2 more with you guys just to see if we can solidify this. I'll do example 10 and 11. So I hope that makes sense, and I'll see you guys in the next video.